We challenge problem number 13, candlebar turbine. We challenge problem number 12, strange motion. Okay, thank you.
Okay, we go on to your preparation time. Now. Just make sure it's turned off.
effect of magnetic field on the water surface as stated in the problem, and also strange motions of the particles. So this is my outline. So let me introduce our experimental setup first. We filled a pressure dish with water and suspended a magnet 2 to 5 millimeters above the surface of water. And next, we drop a styrofoam particle, and then after it lands on the surface, it will start to move. And so, so we then filmed the motion using a foam from below the setup and analyzed the fracture. So next, into our magnet properties. So first we use an N35 grade neodymium magnet with radius Rm and Hm. So it is then suspended above the water at distance d. And so we use cylindrical coordinates due to our axis measuring system. And so next, so as you can see in the video, when we put a magnet close to water, as you can see, the water is deformed. That's because the water is diamagnetic and it's repelled by the magnetic field. In turn, the water surface is pushed down and forms a dent, as you can see with the grids line on the PowerPoint. And so that's considered the energy change of such a deformation. So for a small volume of water, when it's displaced from the dent to the original surface, it will introduce a change in magnetic field energy due to the water being replaced by the air. And since the water is diamagnetic, the energy will decrease. Okay, so when the water is raised to the surface, it will be an increase in potential energy, and this is because the surface is deformed. There will be, and then when the surface is deformed, there will be an increase in surface energy. In surface area, it increases the surface energy. So in general, the water magnetic field will push the water down and support the formation of the dent, while the gravity and surface tension will resist and try to pull it back, as I just kind of explained. And so we have a simplified model here without the surface tension, as it's suggested by the literature. So while we're looking at two other energies at a point on the deformed surface, their competition will give us this equation right there. And so assuming that the magnetic field doesn't really differ that much vertically over the shallow dent, we can arrange to get the simplified expression of the depth z of the dent and also the radial distance r. So this is the model we use to predict the magnetic field, and the assumption is that the magnet is homogeneously magnetized. So let me introduce the measurement of the dent. So we take a picture on the grid paper through the reflection of the water from the surface below, and since the water is kind of like deformed by the magnetic field, the image of the surface will be distorted, and so we can trace the rays back to the grid to find the deformation. Okay, so we know that the position on the grid is and the interest field of our lens. So from the picture, we can calculate the angle of theta of the light ray corresponding to a certain pixel on the camera sensor. So tracing it back, we can find the point at which is reflected by the water surface. Then we can calculate the tilted angle phi of the water surface, and by looking at the center vertical line of the photo, we can center vertical line right here. So we can recreate the tilt angle across the dent. So and then next, we're trying to sum up the depth of the dent. So we also consider refraction between air and water, so we can get the tilt angle. Anyhow, we'll try. So by looking at two neighboring points, these kind of like have a horizontal difference and also a vertical distance. So assuming that the tilt angle is small, we can use like single trigonometry to calculate the height difference. Then we sum up the height difference from far away, which so that should be 0, and then so we can get an actual phi z at position x. So this is the dent that we measure when we put a magnet with radius 12.5 millimeters and height 35 millimeters close to the water. So different color stands for different distance between the bottom of the magnet and the water surface, as stated on the PowerPoint. So first, let's look at the deepest point. So at 2 millimeters, it's going to be at the edge, while at the edge, while 3 to 5 millimeters, it's going to be at around the center. So both experiment and theory show this result, which means our model can pretty much predict the shape of the dents, but it cannot kind of predict the magnitude, so we're kind of going to modify that. So instead of looking at the point at the deformed surface, we look at the whole column that's replaced by that is replaced. And so we also consider the non-uniformity of the magnetic field to solve and then get this equation, so we can solve ZR and to find by the simulation of magnetic field. So next, as you can see, the predicted magnitude is around twice of the simplified model, and it matches the experiments quite well. And so take a look. So if we take a closer look, the curvature is actually sharper than the measured one. So we believe that this is due to surface tension, as it tends to reduce the surface area and in turn reduce the curvature of surface tension. So what we calculated and compared the energy ratio between the magnetic field and surface tension, and found that the surface tension is still within one order of magnitude, and this could cause some discrepancy within our model and experiment. So that's what we think caused the deviation. So we can now look at the two types of motion. So during the inward motion, the particles just kind of move in, and then while the outward motion, the particle will be pushed away by the magnets, as you can see in the video. So the outward motion, the particle kind of slides away from the magnet, and it kind of generally decelerates, and the particle will accelerate towards the magnet and decelerates when it's below the magnet during the inward motion. So they are still quite different motions. So we're going to talk about what caused these kind of motions. So the explanation I have is called the Capillary Force. We read in literature that the particles will be attracted to a meniscus if the slope signs are the same. In other words, if there is a inflection point between the meniscus, the particles will be repelled and vice versa. And so here I will go into more detail about explaining the capillary force. So when a particle is on a flat surface, it should be the surface tension on each side should be horizontally balanced. So when it meets a concave surface, the surface tension will try to reduce the surface area, and so in order to pull the surface up, causing a larger horizontal surface tension to the right, and so now they are not balanced anymore. So it will kind of get attracted to the concave surface. And so when the other surface is concave down, it will try to pull down the water surface, and then so the surface tension will not be balanced anymore. So the same idea, it will get repelled by the concave slope, and then so it will kind of go away. So that's pretty much and we can notice that there should be an inflection point here, so that's kind of our explanation towards the motion. And so now we're trying to find the boundary of the motion. So we can see that this is the boundary that we found of moving out and moving in our experiment. So we did various trials, and then for the inflection point, and then so we can see that in this graph there is an inflection point within our dent. This blue line is supposed to be our dent. So when it's repelled by the inflection, it should move outward, like in this boundary particularly, but that's not the case. You can see that there's clearly a difference right here. So we're going to talk about why is there a 4 to 5 millimeter dent. So as you can see right here, so the explanation that we have is that the blurred lines, this is the picture that we took from below, and so with the blurred lines you can see that there's more deformation, and then with the zebra lines it represents like less deep deformation. So when a particle deforms the water surface more than a magnet, it will kind of like eat up the inflection point. So in that case, it will not move outward again. So we'll have to wait until that the deformation caused by the particle will not be eaten up by the deformation that will not be eaten up the inflection point. So we can see that the steep slope right here is about 4 to 5 millimeters. And so within when we compare like the blurred lines of the particles with visible lines on the then we can see that we can assume that the particle has more deformation. So this is the reason that we have a 4 to 5 millimeter boundary in our experiment. So next, so if the particle, that's the explanation. So we can see well next, so talking about like the FR and talking about the FR of the motion, inward motion. So we can see that these are the forces that are being acted upon the particle. So we can see that when it's like getting on to the view of the dent at the other side, you can see that there's concave surface. So then as we talked about the capillary force, the T1 and T2 will not be balanced anymore. So and then we also have the magnetic force that is caused by the magnet, and the water drag force that will be that will be on the other side of the velocity. So pretty much all of these will cause a deceleration on the particles. So that's why we can see that with a inward, it's negative when it's going inward and it's positive when going outward. But pretty much we have so that's pretty much why we have like different positive and negative forces. And so when we compare different magnets, different height of magnets to the water surface, we can see that the larger the height, the larger the velocity is, and that the more shallow depth will decrease a difference in horizontal component of the surface tension. That's why they have different heights. No, that's not why they have different velocities. And that the particle travels further with a smaller height due to a curvature of the bottom of the dent. So it's going to be more shallow, and then there's not going to be, and it's going to be more curved. So it's going to go to nearer to the end, to the center. And so for the, so if we compare like two magnets that we use, we have like particles that move closer to the smaller magnet. That's because that the dent is kind of different shaped. So for the outward motion, we basically have these forces that's acting on it, and we can see that these, so it's supposed to go this way according to the capillary force, and the others will be dragging it. So that's why we can see a deceleration in our motion. And so, our conclusion is that we can we can model a consideration of the displaced column water, and that capillary force is the primary factor of our type of motion, and inward motion is a combination of these forces, while the green one would be accelerating, and the red one will be decelerating, and while outward motion is a combination of these forces. And that will be my presentation. Thank you. I would say no, it's not.
Okay, can you please turn then to the next slide? So when we're looking at it, if we take into your account the graphic drew on the previous slide, how is the magnetic flux density changing along the axis?
So I believe the magnetic force that's acting upon it will kind of look like this direction. So it's going kind of like outward on the like edge.
Okay. Can you turn please to slide number 14?
Okay.
Oh, excuse me, slide number 14. There was So this is like on this graph. For what model are these lines?
So the lines are used as this simplified model that I talked about, which is from the literature.
Okay. And the said model is based on homogeneous magnetic field.
Yes.
All right. Can you please turn to slide 27? Okay. So what importance is of this graph on the left that I didn't really understand?
Oh, yeah, I'm sorry for not making it. It's basically the whole process, the forces that's active on the particles during the motion, like the whole process of the motion.
Thank you very much. Okay, thank you very much.
Time, you go preparation time of 3 minutes.
the problem was really about a small sprinkle floating particles on the surface of water in a bottle. However, in this experiment, we brought a strong magnet above and near to the water surface, and the point was to explain the observed motion of the particles. To summarize the whole report, I'd like to say something about the theory. The theory was, in my opinion, very good. It took into energy consideration of water deformation, effect of magnetic field, and capillary forces in water trap. We also saw own contribution of the reporter in their additional models. Also, for the experiment, we had a magnet suspended above a petri dish and a visual tracking of paper visual deformation. The reporter identified two main types of motion. So first, I'll talk something about the theoretical model. The main pros of the qualitative explanation and quantitative modeling. However, theoretical explanation of the motion. However, it was a little unclear how the experiment exactly went and what was the calibration factor, and there wasn't a clear theoretical model for quantitative description of theory of particle motions. And about the experiment as a result, again, they were very good quality, well-controlled experimental setup, analyzed relevant parameters except for particles that I would like to talk about in the discussion. Also identified correct boundary conditions necessary for strange motion, and very interesting visual measurement method that I'm really amazed by. And now I'd like to continue on into our discussion, effects of surface tension, magnetic field, homogeneity, measurement method, and calibration.
Yeah, I think, yeah.
Okay, awesome. Can everybody hear me? Awesome. So I'd like to start with slide number 5, where I ask you in my clarifying questions, I ask you about the homogeneity of the magnetic field here. And in your theoretical model, at least the first one, you assume homogeneity. And if we turn to slide number 8, my bad, slide number 5 to 15. We see big difference between the experimental and theoretical data. And I'd like to discuss the size and like dimensions of your magnet. What type of magnet? What do you think? How the shape of your magnetic used in research and its magnetic field affects this phenomenon, because magnets like these usually aren't really homogeneous.
Okay, so the first part of the magnet. So just for mostly when the model that we use, when we meant by homogeneously, we meant like most of the magnetic field lines should be caused like this way, right? But in in reality, it's not going to be always perpendicular at the sides. So we actually, instead of just contradicting, so what I mean by when we put the homogeneous part into consideration, we mean that we actually measure the magnetic field. So as you can see on the page, this PowerPoint, so we did use like a movable portal, and then we keep the magnet in the same place, and so we measure the magnetic field, and so we put our data and like to kind of fit the line into it, and then put it into our calculation to get the second simulation that we have for the dent.
Okay, so you measured and confirmed that it was relatively homogeneous. However, later in the presentation, is it suppose you put out another theoretical model that assume non-homogeneous field, right? So can you please tell me something that why would you propose another theoretical model if this was really homogeneous?
So what I mean, so I have not made it clear, I suppose. So the simulation that we used in the first one would say that it's all homogeneously, so it will actually not have exactly the same magnitude of magnetic field with the real magnets that we use. So in the second simulation, we use the real data that we have to put into consideration of the simulation that we have in order to get a more accurate simulation.
Okay, I think I understand what you're saying. However, can you please, so the other theoretical model, it did not use the data from the first.
Well, the homogeneous one was not a data. It was an assumption made by the simulations that's usually used in computers.
Okay.
Yeah, so it's not from data. Only the second one is the data, which we did ourselves.
Okay, I understand. So now I'd like you to turn to slide where you talk about the first theoretical model found in literature. Sorry, I didn't remember the slide.
Math equation.
Can I see? This one? Okay, this theoretical model that you use in your research suggests surface tension energy is negligible, and I did not understand if in your later theoretical models if they included surface tension.
So for the other, we did try to consider surface tension, but we kind of underestimated it, the surface tension part. So we still have a big. So we can see that in the data points, we can still see there's a magnitude that there's a difference between the theoretical lines and the
experiment. Yeah. Okay. So that's what you're showing basically on diagrams in slide 27 and 28, right? Okay. So what do you think? How would this experiment be affected by using not only one particle but a lot of particles placed on the surface of the water?
Okay, so let's separate particles.
Here you go.
Separate particles into two kinds. So first we want to talk about how the surface tension of the particles should be. So usually particles have two kind of conditions, which is one that will bring the water up like this, and the second one it will bring the water down like this, right? So by using these two different kinds, so what we used here was here. But if we were to use this kind of particles, so according to the capillary force, it will have so if this is a concave here, it will still be attracted. So it will assume that by using this kind of particle, we will have a different boundary of which the motion moves outward and which moves inward. And so another kind of type of particle, as to assume that you're trying to point out, is dimatic particles and paramatic particles. So it would work. So because we use styrofoam in this case, so we're actually use a magnetic particle, I believe. So if we use a paramagnetic particle, it would not. So it will still have. So the magnetic forces that's acted upon it, I assume would be changed in direction. So paramagnetic will cause the magnetic force in that case to change its direction. Yeah, but if I assume that it won't really affect much of the motion, maybe the magnitude, but not exactly how it moves.
Okay, I understand what you're saying, but now what I was really asking is, did you if there is a lot of particles, not only one, if you have a lot of particles, how does the system then act? Is it the same, or are there any other effects that might be affecting because as you said, you're talking about different particles and how they enter the water. So if we have a lot of particles, do we can see the change in the experiment?
Okay, so the first part of the change in motion in the louder particles is similar to what we talked about capillary force here. So another noun for capillary force that so the thing that we're trying to say right here, another name for it would be Cheerios effect. And so if we put a lot of particles, Cheerios effect would also happen. Particles, because they have the same, they have like how they pull up or pull down the waters are the same, so they're going to gather into a big amount. But we did do the experiments on this, but it was kind of harder to quantify. So in the report we only used like one particle, but anyhow, it's going to still move it into under.
Yeah, I understand. I'm just asking because the problem states that multiple particles, but I agree with your explanation. However, I'd like to discuss if we have like this a number of particles, would the boundary conditions and inflection points change?
Okay, so to be honest, what I have here, from my understanding, I would believe that the this amount is actually bigger than the dent that is formed by the magnet, and with multiple particles, they will even attract like higher water surfaces. So I believe that the boundary will probably have to move even more outward for the outward motion to happen.
Okay, thank you for your explanation. I agree with you, and I find it really a good explanation. Now I'm about to jump into something more of an experimental part of the research. I would like to discuss your experimental setup, because even if in your presentation you showed us a couple of blurred lines, and how did you exactly calibrate your what software did you use? How did you calibrate? Because in my opinion, I believe maybe using a laser or something like that would maybe be more precise and more well fitted to this experiment, because we have a lot of motion and everything. So yeah, I'll take it.
Okay, so in my defense, using a photograph, so first part is efficiency, because you can just take a graph, and then so we use like raw therapy in order to like get each pixel that is that of the x and y of each pixel, so we can get it like more frequent, that it's easier for us to get the data instead of like having to use laser. But in the other words, I've also tried the laser part, but to be honest, because the problem statement especially asked us to bring water above to bring magnet above the water surface. So in order for the laser to come in, it would have to come in like in really small angle. And by a really small angle, your laser light can only be it will not be only 1 point. So actually, when it reflects on the water surface, there will be an area in this case. So we cannot really determine like which point we're talking about.
I'm not really sure that I understand what you're saying. So you're saying that when the laser reflects, there is going to be an area of water.
No, so the laser light, it's not, so you will think it as a point. So you will think that it hits a point, but to be honest, it's an area of light, but it's in a really small angle. It will cause a really big area, so you cannot really determine like which point of the water that is actually hitting on.
Guys, you're out of time now. I'm sure there's been a bit of a confusion with the clock, but you're all out.
Oh, okay, thank you very much.
Thank you very much, Jerry. It's not the clock. So we go on to the next phase, please, which will be the summary argument.
Okay, thank you very much. Can I start?
Yeah, ready?
Okay, ready. So I'm going to summarize just in a few points. The main points of discussion were whether using homogeneous or wherever the magnet used in this research project done by my reporter was homogeneous or not. We both agreed that it probably wasn't. However, the reporter clearly explained what happened with the was another theoretical model that they described in their presentations. And therefore, we both agreed that the homogeneity of the magnet field of the magnet used is a relevant parameter. We also discussed particle size and how particles, whenever using one single particle and multiple particles, was relevant to this problem, since the problem states that we use multiple particles. And in the end, we discussed the experimental setup and how they measured their angle of index.
Thank you very much indeed. Well done. So we have the questions from the reviewer, please.
Quick question for the reporter. How did you define terminal motion?
Unfortunately, basically just by eye. So we record like the motion for like maybe 30 seconds to 1 minute around. For so
And how did you define terminal motion?
defining the motion.
Terminal motion. So you did mention terminal motion. How did you define
I don't think I mentioned terminal motion.
Then for the opponent, what key parameters do you think are the most important for this?
Can you speak up, please?
What key parameters do you think are the most important for this experiment?
I think the key parameters important for this experiment are the magnetic field, of course, the strength of the magnetic field used in this research project, as well as some fluid characteristics such as surface tension. But and of course, the third parameter that I said I believe the reporter missed is that particle size is the number of particles.
Were you able to analyze the energy of the particles, like velocity, or were you able to quantify velocity?
I was able to quantify velocity. Yes.
What about the energy of the particles?
I believe that will have to be calculated.
Okay. You did mention hysteresis. Is there a torque? Is there a torque on the particles with the particles experience torque, or does it just displace horizontally?
I don't think it gets a torque, and I don't think I mentioned that.
And were you able to do any error analysis on your data?
So we did various trials, but well, most of them have been like dissipated, so like drop onto different positions. So not in like one particular position.
So no error bars for any of your graphs?
We did like multiple estimations. Yeah, well, in the presentation.
I mean, for the opponent, you did mention material. What do you think would happen if you had a cluster of particles right on the,
I didn't hear, what did you say?
you mentioned the Cheerio effect. What do you think happens when you have the Cheerio effect come right at the plane between the dip and horizontal?
I mentioned the what?
Cheerio effect.
Oh yeah, material effect. Okay, so it interacts with the surface just differently and the size and the shape of the objects we have.
Do you think the particles move towards the center or away from the center?
As we observed in the motion we have like towards us.
For the reporter, did you observe any circular motion of the particles?
Yes, but I did. Yes.
Okay. Yeah, I think we're about on time.
Right, thank you very much. You've got your preparation time now, and the reporter and Tony can sit down and have a break for a minute.
response that the second model was used better due to theory and experiment, and we agree with the reporter where the second model considers surface tension, particle movement, and magnetic homogeneity better than the first. And for the second point that they discussed was particle collision and shear effect. The reporters vary the number of particles impacting particle collision and shear effect. And the reporter's response is that it's hard to quantify, only model with one particle. And we agree with the opponent where the shear effect is quite important in this problem because when you vary the amount of particles on the surface of the water, the shear effect and surface tension will allow you to observe different phenomena. And for the last discussion analysis point, the opponent raised that efficacy of using laser measurement as laser measurement method, and we agree with the opponent where tracking via laser brings more accuracy in data collection, allows for the data analysis to be automated and allows for further quantification of movement. So for missed physics, they did not account for shear effect, accounting for quality and comparing between theory and experimental for multiple particles. And for experimental, they could improve the calibrating setup, improving measurement methods, and varying more key parameters. Thank you.
Okay, well done. And we now hand over to the reporter from them final remarks. Do you have
Remarks for the discussion that we have. So the first thing that we talk about is how do we account for magnet and homogeneity. So we measure the magnetic field that we use of the magnet that we use at different positions and take it into account of our theory. And so we also confirm that the equation from the literature is only like an approximation, and that the simulation of the computers used are not what the reality is. And so interaction with other particles, we did observe the motions at this, so we didn't put it up. But with the particles will gather and then they will still move in together basically. And so for the boundary conditions and inflection points, so surface tension deformation becomes larger that the depth is formed by the magnets. So so we think that a larger number of particles will also increase the deformation of the water caused by the particles, and so it will also affect the boundaries, which will kind of like move it outwards for it to move outwardly. So most of it will be inward motion. So the calibration that we did, so for the measurement of the length, we still think that analyzing the picture is a more efficient way, and then also when we use laser, it's actually like it's not going to be a point, so it's going to cause like an area when it hits the surface. So it's hard for us to determine which actual point the laser is reflecting on, and that it will also so we also have to bring the magnets really close in order for them to form. So when we try to get the laser in, it will have to be in a very low angle. So that's kind of hard. So that's kind of experimentally hard to do. So that's why we use the photograph part. But to be honest, we also tried the laser one. And so for the tangential motion, we did observe it, but it's not really a universal phenomenon. So I cannot make a conclusion towards it. Thank you.
very well done. So now we go on to the questions from the jury.
Would you please report here to show that your simulation to confirm that your experiment is completely adjusted by simulation?
Excuse me? Can you please state the problem again?
Because I found in some presenting which slide you show that you have used simulation. Yes?
Yes.
Would you please show the simulation?
You mean like the codes or?
No. To compare which the simulation is completely adjusted with your experiment.
Okay, so this is the second one. The first simulation would be
And which simulation did you use?
so this graph we use the first simulation, which is from the literature, and for this graph we
Not yourself, no?
this part is not my stuff, but this part is my stuff because we also take yeah.
This is yours. It has been done by yours.
Yeah,
Yes?
so we modify the first one and take it into so change it into ours.
And which simulation?
This is ours. We
Yeah.
modified it from the first one.
I know. For example, use Python or any other thing. You don't know exactly which.
Sorry, I
Are
couldn't.
you asking for the type of code?
Yeah, we use Python to simulate it.
Will you please tell me you use what particle? The styrofoam only one particle?
In the presentation, we only use one.
Okay, one styrofoam and the form. So do you think that the size is important or the mass of the particle is important? Because in your slide, I was unable to see the density of the particles.
Okay, so first thing, we did try, we all use styrofoam particles, but we also use different sizes, and the motion itself will not change. The only thing that will change would be like some other physics parameters, for example, its velocity during the motion, but the motion, how it moves itself will not pretty much change, and that so I believe the density of the styrofoam would be 0.047. G over,
Okay, so that is a critical density in which you form that gun.
excuse me?
It's a critical density. You use the different mass particle, different density particle.
I use one density particle with different sizes.
Okay.
I have a question for reporter. Could you show me slide number 27? Okay. Could you explain me because magnetic force is not parallel to vector B, magnetic direction?
Oh, I'm sorry for the misunderstanding. The B here stands for buoyancy.
Thank you.
I've just got a question for Emily your review. You mentioned hysteresis a couple of times. What do you mean by hysteresis?
I
What
wanted to
hysteresis?
refer to like the movement of the magnet. So moving the magnet closer to the rim, how that would function. Like consistently moving the magnet closer to the rim. It's like the velocity of the magnet.
So the magnet's moving?
Yeah.
Yeah. Was the magnet moving? Can I ask the
No.
question? No. So,
But she did. I think she did mention this is something why I asked it. Or
okay.
okay.
From the presentation of the reporter, what did you get? What did you get in physics? The science behind this presentation. What is happening? Can you explain in one sentence?
So,
The physics behind this problem, the presentation.
okay, the water is repelled by the magnetic field of the magnet, and it causes a dent. And a particle, the whole experiment is about like watching how particles in on that surface act. And what I understood from this experiment is that in some inner circle, particles start to fall inwards, and others start to go outwards.
Thank you very much. And out of time, well done. We have to make our business house done. Okay, I'd like to invite the jurors to present their scores for the report for Chinese campaign. Iypt for the strange motion. And my score is a 7. Stanislav is a, sorry, Amir is a 7. Nina is a 7. Stanislav is a 7. And Karina is a 7. Wow, we agree. Well done, too. Okay, moving on to the results for the opponents. From Andrea, I gave it a 7. Stanislav gave it a 9, gave it a 6. And we have a 5, a 7, and a 7. And then finally, the review, I gave it a 5. Gave it a 5. And we have a 4. Stanislav a 6. And a 6 in Charlie's Gap. Well done. Well done. That's a great round, very interesting. Round of applause. So I'll just ask, Marion, would you like to justify why you put this as 7 or you put this as 7?
For reporter, 7 was a lot of mathematics things. I was good measurement of time. I was good links between theory and experiment. But was some things were missing, and for me was 7.
For the report, I guess I was one of the higher grades. I think for both the reporter and the opponent, top mark, I gave you really good grades for your conduct during the discussion. There was, it was very nice that when you were handing the microphone to and fro and using the board together. I've seen some terrible fights where people have not wanted to share either of those things, but you were really helping each other, and that's really good to see. So that's one of the reasons I gave you very good marks on that. But I thought your questions were good. Yeah, your questions were good, and you obviously understood it very well. You went down with your time management because you should be presenting for 4 minutes. And there was a bit of a mix-up on that, but I think we were okay in the end on that. Dina, do you want to say why you gave it a 5?
Although the short question was well explained and it was aimed to the discussion, but it was not quite relevant. And then in discussion, we expect you should talk about the science behind the problems in each question carefully and tell us your opinion to clarify it more in details. But it was just some question and asking question and answering by the reporter. So I couldn't follow all the scientific idea because of that I asked you to explain the physics behind this.
So we carry on in the same way you gave the floor for the review as well?
Yes, of course, because the time management was not good, and then it was changing the slides next by each other without any explanation, and then it was not the review of review of the position or the discussion to explain in more details.
But it's done something with 6. Do you want to say why you like it?
I think it was very good review, more than average level. My sub points are 1 for questions, 1.75 for review of report, 1.35 for review of opposition, and